in our discussions, we assume that somehow we have this voltage. You remember I said, well, I can establish a voltage here, I can establish a voltage there, so on, so bias and bias. And so I'll tell you later on how I do that. I'm going to start telling you how to do this, but we are not going to finish because you'll see it's not going to be complete today. But I promise you, by some point in this quarter, we'll get to the point that we know exactly how to do this. So we'll go one step closer. So for the next couple of lectures, we'll talk actually about biasing techniques. Techniques to maintain this point of operation and generate those. And like everything else, we start from simple techniques, the simplest approach we can take, and then we look at the advantages and disadvantages of each one and try to improve upon the simple state. And that's the way usually engineering usually works. When you try to design something, you don't want to pick up the most sophisticated topology to do that. You start with the simplest approach that you think might do the job and see if it works. If it works, that's the best solution, most of the times. If it doesn't, then you look at other ways to fix it and look at where the problem comes from. So, now, we saw in our discussion of small signal again this morning that you need to establish this voltage. Now, so what is the easiest way? Let's say you want to make a common emitter amplifier, right? And you want to establish some sort of collector current, ICQ. How would I do it? Well, the way I've shown it so far is like this, really. What I've said is that I put a VBE here, like a battery of a given voltage. Let's say I could do that. Let's say I have this magical battery that I could adjust, whose voltage I could adjust, and say, well, let's do bias things like that. If I do bias a circuit like this, what are the advantages and disadvantages? So what is the collector current in this case? Collector current basically, ICQ, is going to be IS E2 VBE over VT. Now, what are the things that can change here? First of all, first and foremost, is that if there's any kind of perturbation on this voltage, any kind of noise or anything, let's say there's a little bit of noise, there's a little bit of a 60 hertz line pickup or something, that gets directly amplified here and will modulate your collector current, right? So it's extremely sensitive to variations of this voltage, and this is an exponential, so a slight change here can change the current substantially. Right? Let's just give you a numerical example. Let's say I want to design, let's say my IS at the temperature of interest is 10 to the minus 15 amps. And let's say I'm at room temperature. And let's say I want to bias something at 1 milliamp. So I want my ideal ICQ is 1 milliamp. So that tells me what my VBE should be. So it tells me my VBE is VT natural log of IC over IS. Or ICQ over IS. So that's, I can try to calculate. So let's try to get. So it's 10 to the minus 3 divided by 10 to the minus 15. That's 10 to the 12. Natural log, that's 27.63 times the VT at room temperature is 25.8 millivolts, right? Times 25.8 millivolts. That's 0.710. 0.710 volts. Okay? So if I can maintain exactly 0.710 at that temperature, at that IS, and everything, things will, the current will be 1 milliamp. But let's say there will be a 10 millivolt error. So let's say there's a 10 millivolt pickup from the line, or there's a DC error of 10 millivolts. So let's say instead of this, I have a delta V of 10 millivolts. And let's see what that does. So if my VBE really is 0.72 volts, I want to see what my new ICQ would be for the same set of parameters. Right? So let's try that. So it's 0.72 divided by 25.8 millivolts, and e to that times 1e minus 15. So let's try it again. 0.72 divided by 0.02. That's 27.9. Eat that times 1e minus milliamps. So you see that for a 10 millivolt error there, I got about 30% change in the collector current. That's a substantial error. That's big. So the question is, how do I deal with that? That's one. But now, other than that, let's say somehow I could magically maintain this. Am I good? Is this a good way of biasing the circuit? Think about it. What happens if I change my temperature? Well, for one thing, that's kind of obvious one, the VT is really kT over Q. So my temperature changes, VT changes. So for a given fit, even if I could maintain this VB exactly constant, there was no variation, nothing, no change. Slightest change in the temperature will change this current. Now, what is actually worse is that this IS guy has a much stronger temperature dependence than this. It's a very strong functional temperature. We'll talk about the dependence later on, how it depends on temperature. But it's a very strong functional temperature, and things will go completely haywire, just go crazy when temperature changes. In the sense that the values will completely change. You breathe on it, it changes. Okay? So that's another thing. The other thing that I'm kind of implicit, even if the temperature were kept constant, so I say magically somehow I keep this voltage constant, magically I keep the temperature constant, there is this guy, I assume that that's constant, but it can vary from one transistor to the next one. This parameter is very sensitive on the dimensions of the transistors. So actually the physical dimensions, if the actual shape of the transistor is slightly different from one to the other. We saw that you could not make two transistors, so two of anything that are identical. That would result in a variation in IS. And IS would be different, and if IS is different, then the IC will be different. Proportionate. So these are different variations, right, on the thing. So the general three classes of variations that you can have are sometimes abbreviated as PVT. Sometimes say, well, adjusting for PVT. P stands for process, V stands for voltage, mostly supply voltage, and T stands for temperature. So these are the things that we have, and in this example we have all three of them. I have a strong sensitive dependence on this voltage. If I use a voltage source, it's generated off of supply in this case, let's say. I have a strong dependence on temperature, as we saw, and I have a strong dependence on the process variations, IS. So I'm starting with something that's horrible, and we want to see if we can make something that eventually, ideally, is independent of all of these. And it's not very sensitive. So let's start with that. So let's start with this and see what can I do to improve, what I can do to improve this. The thing is that I'm really trying to determine this current through this voltage. But now, what if I try to establish a current in the base first? So how can we establish a current in the base? Well, I can use a resistor, right? So if I use a resistor in the base, let's say this is RB, and this is your RC, and this is your VCC. So the next step would be to use a resistor here and connect it to the supply, so this current will determine that current. For as long as the transistor is in the forward active region, if this is IB, this will be beta I, which is IC. So what is IB in this case? IB is this voltage, VCC, minus VBE over RB. Now in general, if I were to do this exactly, if I were to solve this equation exactly, I know VB is a function of IC, and then I have to write IC in terms of beta IB, and then solve a nonlinear equation. But the good news is that, as we saw before, and we did this numerically before, the dependence of VBE on IC is very weak. So even for relatively large changes in IC, the VBE doesn't change. That's another way of saying that, but for a very small change in VBE, the IC will change a lot. But the reverse dependence is a log dependence. So that's why we say for typical values of current for several milliamps or so, and for this kind of transistor, the VBE is around 0.6, 0.7, 0.8. So if this voltage is 5 volts, let's say, whether it's 0.7 or 0.8, it's not going to make a big difference in this equation, right? Because I'm looking at 5 volts minus 0.7 or 0.75. And you can see it's not going to make a big difference. So I'm not going to just say, well, from now on, whenever I use VBE on, that's what I mean. IB or IC, I can do the design equation. So this is the analysis equation. If I were to design it, let's say I wanted to establish an IC of 1 milliamp, right? If I were to design it for an IC of 1 milliamp, and let's say my beta is approximately 100 in this case, that means that my IB should be 10 microns. Now if that's IB is 10 microns, that tells me what RB should be. So that's going to be 5 volts minus 0.7 volts divided by what? 1 milliamp. So that's 4.7. I'm sorry, not 1 milliamp. 10 microns. So that's 4.7 volts divided by 10 microns. And that gives me 470 kilovolts, right? Because think about it, if it were 1 microamp, 1 over micro is mega. Right? So that gives me mega, so now this gives me a little bit, gives me 100K times that. So for establishing that current, I have to make this 470 kilovolts. And my current, my collector current eventually, would be beta times VCC minus VBE on divided by RB. Okay? So that's what it is. Now, this is a good thing. It's a good design. Well, it's less sensitive on establishing this voltage, the voltage source, because now I've generated it off of a large resistor and a collector supply voltage. So that dependence has gone away, but I still have the dependence on what? Beta. Beta. And beta depends on temperature. And beta, remember, beta was what? Beta was alpha over 1 minus alpha. Right? So it has a very strong dependence on sensitivity to alpha when alpha is close to 1, which is the case for most typical transistors. So again, it's one of those parameters that you breathe on changes. Right? Changes once you kind of change the temperature, touch the transistor, break the wrong God, all sorts of things. Right? Now, so what happens is that you need to really think about this and do something about it. Why did this beta come directly? Now, IC is directly proportional to beta. So if there's a 30% change in beta, which can easily happen with a small change in temperature, there will be a 30% change in IC. So I'm still a little bit better than the previous case, but I'm not there yet. What do I do about it? Where does this problem come from? Because basically it comes from the fact that IB is directly responsible for determining IC. And there's no relation, there's no direct coupling between the two of them. So one way to deal with that, and another way of thinking about it, is that there's a direct gain, voltage gain from here to there, that's quite large, even for variations in this voltage. So you have this strong sensitivity. So I have to somehow kill that, or create this additional mechanism for feedback from the IC to IB. And the easiest way to do that is by basically introducing a resistor in the emitter, an RE. So let's say this is RC, and this is RB, VCC. So now let's look at this one. If I introduce a resistor in the emitter, what happens? Let's try to determine the IB and IC. For as long as the transistor remains in forward active region, and I have to double check that all the time, IC would be beta IB. Okay? And this is IB. Now I can write a KVL, right, from here to there. So I can say VCC, right, minus this voltage drop. What is this voltage drop?
IBRB.
Exactly, RBIB. Minus this voltage drop, which we said for typical values of the voltages is not going to change much. So let's say it's treated as a constant for this calculation. VB on 0.7 volts minus this voltage, which is what?
Beta IB RE.
RE, you could say beta plus 1 IB, really exactly, but it's a beta, approximately. But it's beta plus 1, because it's IE, IB, which is IE approximately, is 0. Right? Because I started from VCC, I went down this one by equation for IB. One equation, one unknown. So I can solve it for IB. So I can write as IB is VCC minus VBE on these two terms divided by what? RE, beta RE plus RB. But that's IB. I'm interested in IC. So I can multiply by beta. Right? So IC is beta times that. So I can divide this denominator by beta. And then I get VCC minus VBE on divided by RE plus RB over beta. So that's my new collector current, expression for collector current. Did I do better in terms of dependence on beta? Yes. Right? For as long as RE is comparable or greater than RB over beta, then I don't have a proportionality. If RE is 0, of course, it reduces to the previous expression, right? It becomes proportional to RB, to beta, right? But now, I have created this term, and if I make RE large enough, then I don't depend on it. This does not depend on RB. In other words, if this is much greater than that one, approximately it will be dominated by this. And that's a good thing. Because now I've eliminated my dependence on beta, I still have dependence on supply, which we'll have to deal with later. But that's kind of reasonable. Now, practically, so I can use something like that to bias a transistor. Or I could do something even slightly better. I can actually try to establish this voltage using a resistive divider. So this is a very common topology. I'm sure if you've done some discrete electronics, you've seen this. Something similar to that. So you actually use two resistors, RB1 and RB2. This is VCC, this is ground. And this is RC and this is RE. And what you have here, in this case, what you're doing, you're establishing this voltage. And for as long as this current, let's say IB, is much smaller than this current, let's say I1, this voltage is what? What is this voltage? It's the voltage divider ratio, right? So for as long as that condition holds, then let's call this V1. V1 is going to be RB2 over RB1 plus RB2 times VCC, approximately. And if I establish this voltage, if I know what this voltage is, what can I say about this voltage? VB on 0.7 on below for silicon transistor, right? For typical ranges of current again. So this is the VBE on. So this one will be V1 minus VBE on. And therefore, if I want to establish, and what can I say about this current, the relationship between this current and that current? They're related to an alpha, but they're almost the same, right, for all practical purposes. So, if I know what current I want, so going through the design equation, let's say I want to establish 1 milliamp, right? If I were to establish 1 milliamp, what I need to do for a given RE, I need to establish this voltage at that level. Let's say I pick my RE to be like 1 kilo. Just let's pick some numeric. So if this is 1 kilo, my 1 milliamp, what would this voltage be? Good? 1 volt, right? 1 milliamp to 1 kilo is 1 volt. This is at 1 volt, above ground. So what does this voltage have to be? 1.7 volts. DC. These are all DC bells, right? So I want to establish 1.7 volts here. Now, I know that if this current is 1 milliamp and beta, let's say, is around 100, what this current is going to be? Ballpark. It's about 10 microamps, right? So to make sure that this current is much greater than that current, so let's say I pick something like 100 microamps there. I want this total current to be 100 microamps. So what does that tell me about my VCC? Well, let's say my VCC is fixed. Let's say it's 10 volts. What does it tell me about the sum of these two resistors? It says, what is the current through this branch if you ignore this current? It's much smaller. Divided by these two resistors, sum of two resistors, right? So VCC over RB1 plus RB2, I want that to be 100 microamps. And this is 10 volts. So that tells me that RB1 plus RB2, the sum of the two resistors is 10 volts divided by 100 microamps. That's 100 kilo. Right? And well, I mean, it doesn't have to be exact that. I mean, if you pick 200 kilo ohms, it's probably going to be okay. If you pick the sum to be 50 kilo ohms, it's probably going to be okay too. Right? So let's just go with 100 kilo ohms. It's the sum of the two. Now I want to establish this voltage at 1.7 volts. So that tells me that this voltage, this resistor should be what? 17 kilo, and this resistor should be 83 kilo ohms. Right? Well, if you go with the scale 12 resistors, right? I mean, there is no 1.17 kilo and 83 kilo, but there are a couple of resistors that are very close to these. Do you remember what they are? So if you don't remember, the scale is 1, 1.2, 1.5, 1.8, 2.2, 3.9, 4.7, 5.6, 6.8, 8.2. That's if you divide the 1 decade by 12.
Must have missed that.
If you actually take it in log domain, if you look at a decade, so if this is basically if you have a log x-axis,
No,
right?
I understand. I mean, nobody's ever told us, and that's how the resistor convention works.
Right. No, you can divide it in different ways. You can divide it actually by 12, or you can do it by 24 or something like that. So if you divide it by 12, like to an equally spaced thing in log, those are the numbers you get. I mean, they're close to what you get. So they're not completely arbitrary. Anyway, so there's an 8.2 and 1.8. That's the point. Of course, you can try to kind of make exactly 1.7 by kind of taking 1.5 and 300 kilo, or 200 kilo, 100 kilo, 100 kilo, or just like 1 kilo or something like that. But let's not bother about it. Let's not worry about that. So I make this, I think it's good enough. 8 kilo, this is 82 kilo ohms. Okay? Oh. Now, I'm designing, right? This is a discrete circuit I'm making. So now I have to also pick my RC in this case, right? How will I pick my RC? First, remember, I'm looking at this from a DC standpoint at this point, so far.
You don't want a thinner saturation.
Exactly, exactly. I want this to be a good point. I don't want it to be too low for this guy to go into saturation. And I don't want this voltage to be too high. Because if it's too high, then I don't get much swing. So basically, I want to see how low I can go on this one. And how high I can go. And put it exactly in the middle. Or close to the middle. Because that allows me to have the maximum range of kind of unperturbed or kind of undistorted range. Right? So let's see, well, the upper end is very clear, right? But how high can it go? VCC. Because if the current is 0, it basically goes to 10 volts. So that the top end is clear. How low can this go before it hits a saturation?
VC should be about 0.2 volts.
Oh yeah, so it's VCE 0.2 volts. And when this goes down, basically it means that you're drawing more current than the operation point. This is your IQ, right? Or VCQ. For it to go down, it has to actually get to that point, right? So it has to actually, if this were to be halfway through, this would be twice as much current. Ballpark, right? Remember, this is zero current. This is the quiescent current. To go down by the same amount as I went up, I have to draw twice as much current out of this resistor to go that far down. So this is probably around 2 milliamps, right? So I bias it for 1 milliamps. At 2 milliamps, I have to see what the voltages are. So that gives me the lower end. So at 2 milliamps, this is at 2 volts. And this is about 0.1 above that, let's say 2 volts, 2.1 volts. So it's somewhere between. So this lower end is 2 volts, this upper end is 10 volts. I want the midpoint to be exactly between. So what should that voltage be? 6 volts, right? To get the maximum range. Fair? Does it make sense what I'm doing? So it's 6 volts. Now, it's 6 volts. So for this to be 6 volts at 1 milliamp at the quiescent current, what should this resistor be? No. It has to be 6 6 volts, so it means that it's 4 volts below VDD. This voltage has to be 4 volts. It has to be around 4K. I don't have a 4K resistor. What do I have? The 3.9. It's somehow magic. It works out to be very close to the numbers you know, right? Yeah, I just played with some of the
Or
numbers.
you use a pot. Or you just use a pot.
Yeah. But this is okay. This is good. Okay, so now this is the basic circuit from a biasing standpoint. Now, if I want to make this into an amplifier, a real amplifier, okay, how do I do that? Well, I need to apply the signal to the input first, right? So where's my input? Can I just put a voltage source here, my signal generator, and attach it here? What happens if I do that?
The biasing.
Yeah, it will mess up the bias, right? Because this is kind of from DC perspective, it's a short or a very low source impedance, low impedance source. So it messes up this point. So I have to somehow get the AC signal in without affecting the DC operation point that I've worked so hard to establish.
Coupling capacitor.
Yeah, I can use a coupling capacitor. So this has to be a large capacitor. You know, some of my colleagues like to call it the big fat capacitor. Okay, so now here, the source unit you apply here, and this is the Vn, and in general your source has some sort of source impedance, right? So let's say you have a source with a source impedance of 1 kilo ohm. That's not important when we talk about AC. So this is really your source. So the source is in the box here, and that's inside there. So that's the effective source resistance. It's maybe much smaller, but let's just say that's what it is. And now I also have a load. So let's say I want to kind of drive something, let's say a loudspeaker or something like that. I want to make an audio amplifier. So that has some sort of impedance. Well, in general, the loudspeakers have very low impedance, right? So let's say 5 ohms, 8 ohms, or 4 ohms, and all those things. But let's not deal with that because I know I can make a buffer to deal with that. Then it messes up my gain. So assuming that I can put some sort of buffer, so what the impedance I'm looking at is relatively high. So let's say it's a 10 kilo ohm. But I know this is really the input impedance of the buffer that drives the load. We'll get to that too. For now. And I need another capacitor here, right? Because again, I don't want to short this to ground and mess up my output. So if I were to design a discrete circuit like this, I need another big fat capacitor. It has to be big enough to let all the frequency, the lowest frequency content of this thing to go through without distortion. And we'll talk about how these things will affect the frequency response next quarter. So if I use this circuit like this, as is, what is the gain? Let's go and try to calculate the gain. So we've designed a circuit, at least we need to be able to know what it's supposed to be, right? What its gain is. So how do I do that? There are 2 ways to do it. Actually, let me show you the way I do it, and then we'll draw the small signal model. Okay? I'll do a very quick one without drawing much. So, I want to calculate the gain of the from a small signal perspective. So, let's do this, look at this, because I don't want to do it the other way around. I say, okay, I need to know what's the gain from here to there. Okay? So, the gain from here to there consists of 2 parts. The gain from here to here, and from here to there. I need to calculate what the gain is from here to there first. It's a product of these 2 gains, right? Let's call this V1. I mean, in my mind, I think about the small signal V1. And this is V in, and this is V out. Okay? The perturbations on this node now. Say, okay, the gain from here, from a small signal perspective, from an AC perspective, I've made this capacitor large enough so for the AC signal, it's a short. So I don't need to worry about that. So, why is there a non-unity gain from here to there? Because there's some load resistance here, right? There's a resistance here, there's a resistance to ground here, there's a resistance to AC ground here, there's a resistance to AC ground looking into this guy too. So the total resistance on this node to ground, other than what you see to the left, to the right, is the parallel combination of this guy, that guy, and whatever I see looking into the base. So I'm not writing anything so far. What do I see looking into the base? I remember the reflection rule. Whatever I have in the emitter multiplies by beta, plus 1 beta, and plus whatever. So significant. So it's about 25, at 1 milliamp it's about 25 ohms, plus 1 kilo ohm. That gets multiplied by 100, right? So that's a factor, that gives me about 100, and that gives me 102 kilo ohms. Ballpark 100 kilo, right? Ballpark, I mean, I don't even think about Rm. Ballpark is about this guy times beta. 100 kilo. So I see 100 kilo ohm, I see 82 kilo ohm, and I see 18 kilo ohms. So it's a parallel combination of those two. I could try to sit down and write them down, put them in a bunch of my calculator, but I know 18 is more substantially. So the parallel combination of 182 is probably going to be around 40-ish or so, about half of the smaller one. And so it's 40 in parallel with 20, that gives me about 14, 13, 15, 13. So it's a voltage divider between 1K and 13K. So that's 13 over 14, so that's probably something like 0.92. So I know the gain from here to there, 0.92, 0.3. I mean, maybe wrong, so we'll see how off it was. I don't remember what the numbers are for this example. So now, and then I have to calculate the gain from here to there, right? That's a relatively straightforward thing because I've already talked about this. This is a common emitter with emitter degeneration. So it's the total resistance in the collector by the total resistance in the emitter. What is the total resistance in the collector? I got that 4K or 3.9K in parallel with 10K, right? Because the 10K, this is short, and from an AC perspective, these two are in parallel. But this is AC ground, this is AC ground too. So it's 4K in parallel with 10K, that gives me about 3K probably. Right? Ballpark. 3K divided by 1K plus something, so let's say 1K, so it's about 3. So 3.9, 2.8. I would approximate this gain to be 2.8. We'll see how far off I am. So that's the way I want you to learn to do this, if you can. Okay, so now let's do the small signal analysis. So from a small signal perspective, what do I have? I have the Vn. I only look at the perturbations, the AC part, right? I have the 1K. If I pick the large enough capacitor, I don't have to worry about that. It's a short. Then I have two resistors to ground, RB1 and RB2. Both are connected to AC ground because they don't change. The VCC doesn't change either. And then I have the input of the transistor. So let's look at the. So I have alpha Rn. I have Re. I have alpha IE. I have RC. In parallel with RL, which is 10K. This is V out. And this is V1 and this is Vn. Right? Again, the same deal. It's a voltage divider between these guys. So I'm interested in this, VO over VI, or V out over Vn. Right? But I write it as V out over V1 times V1 over Vn. And I calculate these individual gains independently. Right? So this guy is what? This is the voltage divider ratio, right? So it's the parallel combination of RB1 and RB2 and whatever you see looking into here, which is what? Which is R pi plus. Do you mind if I just use beta instead of beta plus 1? No, it doesn't matter, right? Beta Ra. So we have with Rm plus beta Re. I'm sorry, R pi, yes, thank you. Divided by RB1 in parallel, RB2 parallel with whatever, R pi plus beta RB, I'm sorry, beta Re, plus Rs. Okay. Well, I have to do this parallel combination this time. So first I have to calculate this. So I know this is 100 and this is 2.5K, so that's 102.5K. And RB1 and RB2, so I have to calculate the parallel combination. So let's put that 105 times, was it 83, 82? So that's 45.6 times 18. 12.9. This thing is 12.9 divided by 12.9 plus 1. So that's 12.9 divided by 13.9. That's 0.929. What did we have there? 0.9. Okay, well, it's 0.93. Okay. That was close. I swear I didn't remember. Now, the other thing is, so now, that's the gain from here to there. Now I have to calculate the gain from here to there. So that gain is RC in parallel with RL divided by RC in parallel with RL plus, divided by RE plus RM. It's really alpha RM, but I'm saying R. So RC in parallel with RL is 3.9 times 10 divided by 13.9. That's 2.8. 1 kilo ohms, and that's 1 kilo plus 25 ohms is 1.25, so that's divided by 1.025, that's 22.7, so this gain is 2.74, and that's 0.93 times 0.93, that's 2.55, so we said 2.8 plus 3, 2.55, 2.6. Okay? So, and that's true. I mean, if you make that circuit, really, take any kind of basic NPN transistor and make that circuit, you will see that kind of gain. You can go and make breadboard yourself. Now, well, okay. So let me quickly do one. The gain is really low, right? So 2.8, 2.7. Why is it? Why is it so bad? Well, if I hook it up to a microphone, it's not going to give me much signal. But what is killing my gain? This is supposedly a common emitter. I should be able to get more gain out of it.
You gotta read up to that beta.
Say again?
They only get read up to beta.
Well, we kind of, yeah, true. I mean, we got rid of beta somehow. Well, how did we get rid of beta? This guy, right? The effect of beta we got rid of through this guy. So basically, we have degenerated this, right? And it's no surprise. I mean, if I just look at this alone, the gain can't be more than 4, right? Because this ratio is less than 4. And then I have this voltage divider at the input and all those things. So they tax it all, and so at the end of the day, I have to talk about 2.6. So the problem is this guy. This is killing my gain. And that's exactly how it was helping me with the bias. So is there a way to have my cake and eat it too? Okay, yeah. So I want this resistor to be there from a DC perspective because it helped me with my bias, right? It got rid of my beta. But from an AC perspective, I don't want this here at all. It's just a horrible thing to have. So I do this. I mean, one way to get rid of it from an AC perspective is just to put another big fat capacitor here. And from an AC perspective, you shunt it. It just basically becomes short. It becomes a non-degenerate common emitter amplifier. But from a DC perspective, it's there and it makes sure that my bias is established in a stable way. And this is probably a circuit you've seen before. This is probably the most basic way of implementing a discrete circuit. So from an AC perspective, though, what changes in the circuit is that this goes away. This is not there from a small signal perspective. So now I have to redo my gain calculation. So let's redo it. Again, I could do it using that. So let's just look at it from here again. Do it on the fly here. So what changes for this part? Would this part change? V2V into V1? No. Yes.
Yes.
Yes. Why does it change? This part, this impedance, is changing now. Because it's not beta RE anymore, right? It's just R pi. So now instead of being about 100 kilo ohms, it's about 2.5 kilo ohms. So it's 2.5 kilo ohms in parallel with 18 kilo ohms in parallel with 82 kilo ohms, it's about probably 2.4 kilo ohms. Right? It's almost 2.5. So it's a voltage divider between 2.4 kilo ohms and 1 kilo ohm. That's about 2.4 divided by 3.4. So that's probably about 0.6. No, it's actually more. It's more like 0.7. So gain is about 0.7 times. Now, but now the good thing is that the gain from here to there is really the ratio of this guy to Rn, or GMRC. Well, GM total RC. Right? Because from an AC perspective, this guy is not there. This resistor is not there. So it's the GM of this guy, which was 40 millisiemens, times, as 1 milliamp, times the parallel combination of these two resistors, which we said was what? 3? Approximately 3. So it's 3 times 3 kilo ohms times 40 millisiemens is what? Million kilocandles, so it's 40 times 3, it's 120. So that's times 120. So what is that? 0.7, it's about 80 something. I would estimate 85. Oh. That's fair. Although I lost on this one, I gained a lot more on this one. So let's do it here. So let's do it exactly. So in this case, again, the voltage divider ratio is between the parallel combination of these three. Now it becomes R pi in parallel with RB1 in parallel with RB2 divided by R pi parallel RB1 parallel with RB2 plus RS. So it's a parallel combination. Okay, so it's 18 times 82 divided by 100, so that's a parallel combination 14.8 times 2.5 divided by 17.3. 2.13 kilo ohms. That's the numerator. So 2.13 kilo divided by 2.13 plus 1 kilo, so it's about 2.13 divided by 3.13, which is about 0.68. So we said 0.7, 0.68, so it was not that far off. And now the second part is basically GM RC parallel with RL, which basically becomes, we have to calculate that. So it's 3.9 times 10 divided by 13.9, 2.8 times 40, that's 112, okay, times 0.68, that's the product, the total gain is going to be 76. That's it, 85. Okay, so that's again, I mean, that's a respectable gain, 76. And again, if you make that circuit with that capacitor, and without it, you will see that there's a major difference in gain, just because of that, because it removes the degeneration. Okay, now, I think we're out of time, well, we may out of time, but any questions about this? Yes?
The small signal model, like from now on, is it just going to help us calculate the AC? Like,
That's the only thing it will help.
okay. Because like I never learned like a small signal model in my previous school, so it's just, I think they didn't like to use it in the book.
Right. No, this is a tool, an additional tool to help you with AC calculations. Right. And it also allows you to think about it. But you can never use it for DC operation point calculation. Never ever calculate the quiescent current with DC small scale. You're guaranteed to be wrong. If you do that, that's wrong. It's only perturbation method. I can't be more bad. Now, what we'll do next time, we'll talk about methods of biasing in integrated circuits. So far we've talked about discrete circuits. We'll talk about integrated circuits, and we'll talk about methods of biasing there. And we'll see how biasing is dramatically different in integrated circuits. And it really goes back to the fact that in discrete circuits, you are trying to optimize for the minimum number of transistors. The transistors are the most expensive component. So you can use resistors and all those things, and you're trying to minimize the number of transistors you use. Because you pay for transistor, per transistor. You'll see in integrated circuit design, the mentality is that you can have as many transistors as you want. And when you use them, you will come up with different kinds of biasing techniques that are more suitable for integrated circuits. We'll see those next time. Bias, current mirrors, and independent. And then eventually we'll see how we can make, at the end of this kind of, I guess, next session or the next lecture or something like that, we'll talk about truly the bias circuitry that's very independent of process, temperature, and supply variation. And it's not zero dependence, but it's very low dependence. We'll see how those things can